Welcome to FEA Journeys, an FEA Academy podcast dedicated to sharing the experiences of seasoned engineers who have achieved success through finite element analysis. In this podcast, we will focus on highlighting the personal stories and the professional path within the FEA domain, catering to both aspiring and experienced engineers interested in exploring practical applications and achievements in FEA. In this podcast, you're going to hear individuals from different sectors of the FEA industry, including FEA software company, FEA consultant, companies that design their own products using FEA, and companies offering engineering services. These interviews will showcase diverse backgrounds and career journeys within the FEA field. For this episode of FEA Journey, we speak with Claudio Gianini. Claudio worked as a structural engineer in various companies such as Firema Trasporti, Alenia Space, now Leonardo, Aermaki, now also Leonardo, the Scuderia Ferrari, Dallara, Toyota F1 and Sauber F1. He worked also as a consultant for structural design, mainly for the ITER project. And in 2014, he created CG CAE, a consulting company for structural design. Claudio is also very active in engineering disclosure since he published almost 30 articles about the usage of the finite element method. Claudio is also the author of the book Computational Structural Engineering, where he provides the necessary information for the correct usage of the finite element method. Thank you, Claudio, for accepting the invite to talk to the FEA Journey podcast. I am very excited today to talk with you. So it's clear that your journey in FEA is one marked by innovation, expertise, and a deep passion for the field. So I'm very, very happy to have you today with us for this session.
Thank you for inviting me, and I am very happy as well to talk to you about the FEA world.
Yeah. So it's very special for me today, this interview, because I talk with you as an author of a book, and I have to present before to go into the interview. I want to present your book. I love this book, Computational Structural Engineering by Claudio Gianini. It's an amazing book for people who want to learn FEA. A lot of very, very good content, about all the stuff about finite element analysis, what you have to do if you want to do a good simulation, if you want to also to learn the good practices. It's very well written, very easy to understand, very easy to follow, and a lot of various topics, linear, non-linear, for sure, a lot of example around Formula One, but I love it because as a huge fan of Formula One, he's very good. And to be honest, I have been very impressed by the two names on the cover for the introduction, Rory Byrne and Luca Marmorini, which are amazing engineers who had a huge impact in Formula One, especially for Ferrari. And as a Ferrari fan, it speaks to me, So thank you for writing this book. I know it's still available on Amazon, correct, Claudio?
Yes.
So, but we're going to talk a little bit about the book at the end of the interview, if you don't mind. Okay?
Yeah, no problems. And thank you for your words. They are more heavy, so to say, by an author, also from your side. So
my pleasure, Claudio. My pleasure.
It's really encouraging in trying to do better. And I think it's still possible. So
yeah.
Next edition, maybe.
Sure. So Claudio, let's start by going back to the beginning. Okay, every great career has a starting point for everybody, and I'm sure that the audience would love to know more about your background and how did you first become interested in finite element analysis, and what were the early influences that led you to this field of finite element analysis?
Yeah, I think it's quite weird and strange what I will say. I was, I think, the second year in university at Politecnico of Milan. So it was 1999, no, 89, sorry. I'm making me younger than what I am. And I think I was in the period where you are doing the propedeutical exams. So nothing really practical, nothing really with engineering. You have a lot of math, geometry, and physics, chemics, chemistry. Yeah. And I think I have seen on a technical magazine dealing with computer graphics. The name was Pixel, an Italian one. And there was the advertisement of one of the first, I think, commercial FE codes for personal computers, which was Cosmos.
Cosmos. Oh, yeah.
And there was the color picture with stress plots, as we know now very well, of a crank, of an engine crank. And I think it was that when I said, yeah, I want to do that. It's not because of the colors, but for me, when I started studying engineering, the engineer was the one who was clearly designing, calculating, and doing all the stuff mainly on his own, which is not really possible anymore in our days, even at that time. But I knew I wanted to do something which was related to solid mechanics, stress, and that's it. And since then, I tried to follow everything with the courses that were available at that time at the university to go into this path, into this route. And I never moved from that. The beginning of my working career was difficult because of that, because it was 1992 when I graduated, and it was not so common for companies to have inside their design process calculations done with FE codes.
That's correct.
And I struggled to find my way. I changed, I think, 3 or even 4 companies in the first 2 years before finding the one where they were doing FE seriously for railways, and I started there actually using it as a professional and not as a student anymore.
Okay, I understand. So that's very interesting what you said, Claudio. So you mean that even engineering company were reluctant to use finite element analysis for the product developments, correct?
Yeah, that's correct. In the mechanical side, when I joined that company, which is named Firema, I think it exists, still exists. As
I think yeah.
Company
I know the name.
From others.
Yeah.
There was a consultant which was coming from the aerospace field, and he was saying amazing things about how they were doing stress analysis, and I learned a lot from him.
Okay.
He was 10 years older than me. He had already experience in aerospace, and the company that he worked for closed up, and he recycled himself in consulting for that company. So we all us in the office learned a lot from him. But yes, to do proper stress analysis with simulations, which were not called simulations at that time, you had to go into these big companies, aeronautics. And in fact, is what I did after Firema. I went to Alenia, which is now Leonardo, the space company in Turin. And I worked on the Node 2 of the International Space Station, which was amazing as well.
Wow. Yeah. And then here you had the chance to use finite element analysis intensively, correct?
Yes. Even if there was still linear analysis for many reasons, but it was the time. At that time, it was good. Even at Firema, we were doing only linear analysis. We did a lot of fatigue because those railways vehicles have to last 30 years more.
Yes,
and more.
Absolutely.
You do proper fatigue calculations, you do strain gauging testing, and you do a lot of things, even in a sector where you might think that saving mass or whatever is not that important as an aircraft, but actually it is. And for strength reasons, you have
absolutely. Absolutely. Yeah. Very, very interesting to know this path. So, getting started in FEA, as you said, can be a daunting experience, especially in the earlier days when the tools and the techniques were less developed than they are today. And
Much less.
you mentioned that. What were some of the key challenges you faced in those early years, and how did you manage to navigate through them?
I think the most frustrating part was meshing,
Okay.
because we had as a common tool the code from Algor, SuperSAP,
Okay.
which now I think is integrated in Autodesk or whatever Inventor. So the
Okay.
Algor
Okay.
company does not exist anymore. It
Yeah.
was a very powerful code in the sense that it was not really user friendly, but you could do a lot of things, strange things, just by command lines.
Mm.
But meshing was really a mess. So dealing with rolling stock material, models were mainly made out of shells. So the bogies of wagons or locomotives were done of sheet metal, which was then welded. And the designers were using AutoCAD in 2D. So
Okay.
it was just electronic technigraph, so the drawing table, but just electronic.
I remember that. I have seen that also at the beginning of my
We
career.
got the DXF files
Yeah.
of the shapes, so
Yeah.
with the different views in 2D.
Exactly.
And I remember for me myself, we
Yeah.
were using AutoCAD again to generate by hand each single element into a
Okay.
DXF file. And then Algor had a sort of preprocessor which was reading the lines, not even the elements, just the lines.
Ah, just the lines. Okay. I
And then
see.
he was generating the elements by the lines. But then you had to
Okay.
place two sheets into different layers and then connect them so the nodes needed to match. So you need to take a lot of care about merging nodes and not having free edges. And
Absolutely.
yeah,
I
and
guess.
even small models, well, which we think they are small now, but I mean maybe 2,000 nodes,
Mm-hmm.
three. So with the shell elements less than 20,000 degrees of freedom, they were taking the whole night. So you were running it maybe at 6 o'clock in the evening and
Right.
go home and then coming back in the morning to see the results. And if you missed something like a boundary condition and the model was not properly constrained, you got just errors and you had to repeat the thing and you were losing one day.
Yeah.
This was the most challenge, and changing the model when you required to, maybe you were seeing that you had to change a fillet because the stress was too high and you had to increase it. You had to redo the mesh by hand. It's not just like nowadays
Yeah.
just click, say, hey,
And when you say by hand, it's really by hand.
by hand.
It's
Yes,
you.
yes.
You didn't have any interactive interface to do your machine, correct?
No, it was
Yeah.
just element by element. So
Element by
once
element.
inequality, then maybe moving one node, taking the lines together.
Okay. Yeah.
But
And calculating the position of each node, correct?
yeah, yeah. Well, that one luckily not to the point where I did it at the university on the paper with all the, how do you call them? It's millimetric paper in Italian, but I don't think it's the same.
Okay.
Where you have
Yeah.
all the divisions and you scale your model and you place your nodes and then you type the
Yeah.
coordinates into,
Yeah.
into an input file. Yeah, good old times. Luckily, not with the perforated.
Oh yeah.
I think that 10 years earlier it was the common practice.
Yeah. I remembered when I started my career 25 years ago, I worked with an engineer who worked on the Concorde, okay, the supersonic
Yeah,
aircraft, and he told me that the finite element analysis was done with those punch card, and
punch card. Yes, yeah,
the
that's
punch, the famous punch card, and so
yes, yes.
and it was amazing because it was maybe for the complete aircraft 5, 6 load cases maximum,
Yeah,
because one load cases it was 1 week of calculation.
yeah,
So those guys they were smarter than us because
for sure.
They didn't have they didn't have the chance to run many simulations, many calculations. They had to be right the first time. Okay,
Yes,
so I think we lost this sensitivity, because it's very easy for us now. Okay, I did a wrong mesh, or I put the wrong boundary conditions. I modify it interactively. I rerun. I have the result in few seconds, for few
yeah,
minutes maximum. So
yes.
it's much easier for us, but we are less smart than the old engineers. I think.
Yeah, I think everything has gone to a certain limit. Now, probably a proper usage of these tools will give a much better product than what it was, and
Absolutely,
lighter and stronger.
absolutely,
But
absolutely.
the risk of that is really losing the contact or the liaison with with real solid mechanics, because in the end
Exactly.
those are models.
Yes, yes. It
So
is the risk. Yeah, absolutely.
it is really risky, but it works.
Yeah, you're right. You're right. But we have to make sure that we follow the right process, and
Yes.
we because and you know that finite element analysis always provide give a result, even if we ask the wrong question. We always have we always have a result. So it is the risk also of the
Yeah.
of the
Yeah. In
method.
our days, is also even worse than in the past, because maybe you have an unconstrained model and some codes just put some springs here and there
Yes,
to make
absolutely.
the matrix positive definite,
Yeah.
which is
Which is wrong.
exactly.
It gives wrong result, but yeah,
Exactly. At least tell me what you've done, and
yeah,
maybe I check. But yeah, I think there was one code I used, and I
yeah,
found out that they're applying maybe not so big numbers on the 3 degrees of freedom, but
yeah,
still it's something that maybe you didn't want. So
exactly. Yeah. Thank you for sharing that, Claudio. Very interesting. Uh, I know that you work on a variety of projects during your career, and I have a question into phases.
mm,
Maybe you could summarize the project you work during your career, and could you share a memorable project where finite element analysis was specifically instrumental in achieving the success of the project, and what was unique about that experience, and what role did FEA play in this project? So maybe start with a summary of the different projects, the major project you worked on during your career.
yeah. Well, I mentioned railways, so I had the opportunity to work on a locomotive for the Italian railways, and we did all the project. I was involved in the motor buggy,
Hmm.
that part. So I followed the calculation together with the designers. So we came to the project. We went to testing in fatigue with strain gauges to check and correlate our models, which
Hmm.
was quite rough because of did by hand, and the calculations were, as we said before, not so performant.
Hmm.
And for sure was something interesting. Then I mentioned the Node 2 of the International Space Station when I was with Alenia Aerospace, so now Leonardo. And Alenia took over the project from Boeing because for some reason they failed something. And
Okay.
yeah, so it was that opportunity for Italy to work on the International Space Station. And then after that, I joined for a while Aermacchi, which is now Leonardo, still also that one. And they were changing from the military sector to the civil aviation. So it was a
Okay.
transition, and did not have a big opportunity to do recordable stuff. But I
Okay.
stayed there, I think, only 1 year and few months, because then I got the call from Ferrari.
Okay.
I followed I followed that
It's a
since.
call you cannot ignore, I presume.
No, of course not. But I was following that since when I graduated. So I sent my CV after my degree.
Okay.
I got after 1 year, maybe I got the possibility to go there for an interview because, at that time you were sending letters, not emails.
Exactly.
They didn't have any pictures. So I got an invitation to just give a face to the CV I sent. And then again, after 1 year or 1 year and a half, I was called for an interview to join the Formula One group, Stress Group, which was starting to be built, and it was 1997, and they started building it in 1996 when Ross Brawn, Schumacher, Rory Byrne joined Ferrari. But unfortunately, I didn't have the experience they wanted, so they wanted someone who was already into the F1 business, so knowing how things are going, that you need to work maybe some days 14, 16 hours because you need to give a result because the race is. And so I lost that opportunity. But then in 2000, I was called when I was at Aermacchi. It was really funny because we changed home. So we left Milan and went closer to Aermacchi, and also my ex-wife now, was working closer there. So we bought a house there. So I called the HR in Ferrari, said, I wanted to tell you that I changed my phone number, my address. And the guy said, oh, it's funny to say because I wanted to contact you. So that
really?
Yes. What about coming for another interview? And okay. And then that was my time. I did the interview with the same manager that was at that time there. And he reminded me, he said, I think, but why didn't we hire you at that time? And I said, because you wanted someone with experience. So now it's different because we have a little bit more time. So you have the experience that we want to have.
I understand.
And we will train you in what is necessary to know for F1. And so in June 2000 I joined Ferrari. And there it was really, I walked 1 meter over ground for 2 years probably. It was really a dream becoming true in the end. And there the project that was really challenging, where FE played a huge role, was given directly to me by Rory Byrne. And he had this intuition, I don't know where it was coming from. Geniuses, they don't really know exactly why they come to a certain idea. And he wanted me, in this case, because I was involved into the suspension calculation, he wanted me to double the camber stiffness. So the camber angle is the one which says or tells you how the wheel is straight with respect to ground. And this one is playing a big role when you corner, because, of course, with the compliance of all the system, this angle changes from the straight end of the straight entering into a high-speed corner. And he said, okay, I want you take with the vehicle mechanical guy, vehicle dynamic guy, you take the highest speed straight that you have and the highest speed corner, and you will have the camber variation between these two conditions. So we identified the old Barcelona end of straight and the corner. This was the highest we could have from telemetry.
Understand.
And then I worked on everything: upright, hub, wishbones, so the line elements which connect the wheel group to the chassis and to the gearbox at the rear, so both front and rear. And I started with the upright because at that time, the front one, because at that time it was made with tie sheet, which was welded. And
it was not composite.
It was not. No, the upright. It was not composite. I think McLaren did some trials, but it was at that time too difficult, and I think now it's even forbidden by regulations. But we started with that because they were not able at that time. Ferrari, we were not able to run ceramic bearings at the front.
Okay.
They were simply failing before 300 kilometers, so it was not the case to risk it into the race. And I started from the existing upright and using Sol 200 from Nastran, which is the optimization, trying to to change the thicknesses of all these sheet metal to get an upright which was stiffer.
Okay, I understand.
And we then used one of these by welding some things on top of it, and it was, I think, 10%, so far away from what Rory wanted, but this was just only one portion. And they asked Schumacher to test it in Fiorano, so the racetrack close to Ferrari. And after the few laps, he said, I don't like it. And the guy in charge of the testing there told him, look at the timings. You are quicker. And he said, I don't like it. Yeah, I'm quicker, but I don't like it. I don't feel the car like it is good. Then Rory Byrne said, who cares? It is because we did it only on the front. If we balance and we do the same on the rear, the car will be more balanced. Okay. So then we had to go. And as I said before, I worked on everything. The upright, we did it in a new complete shape. Wheel bearings, I worked with SKF. Hub, all the wishbones, and the designers, which until up to the year before, they were always said, you have to go down with the mass, go down with the mass, go down with the mass. And we were going up and up and up and up, because, of course, increased stiffness, either you change material. And indeed, we used, for the upright, we used the metal matrix composite.
Okay, it was authorized at this time. Now it's forbidden, but it was authorized.
Okay. No, this is what you meant. So metal matrix, not composite.
Metal matrix,
Yes. It was costing like, I don't know, but it was stiff like titanium and light as aluminum. So, and they couldn't believe it. And then I was telling, you have to increase this. No, but this is another 10 grams. I think we added on each wheel group like 2 kilos, maybe. So the car was heavier, but it was amazingly reacting.
Okay.
It was really...
In terms of handling, you mean?
In terms of?
Handling,
yes.
Yeah.
It was really...
For the driver,
yes.
It was easier to put the car at the right position on the track.
I think the first outcome... No, sorry, the first test from Schumacher on that new car with everything which was done, he was already, by just doing nothing, 1 second quicker in Fiorano, which is...
1 second?
Yes.
It's
because
huge.
it was just above 1 minute, the lapping, and he did it in 59 seconds. So it was amazing.
Yeah, in Formula 1, 1 second is huge.
It was actually... For sure, it was a combination of many things. It was probably the good aero, and then, but I mean, this is the proof that making a thing the lightest you can do it with respect to strength is not always the good thing. And it was possible, because we stiffened up everything, to use ceramic bearings in the front, which are stiffer, because you had stiffer surroundings and they were not deforming that much. I think that is for sure one of the best things I have done. And the year after, he said, okay, we do it again. It was not possible to achieve it, but we increased it again. And that in 2002, I think, was the quickest. It's when we won. No, we already discussed about that on LinkedIn. We won in Magny-Cours in June.
Oh yeah, I was there in 2002. Sorry, I was at Magny-Cours when Schumacher won the World Championship. I remember that.
That was, I think, the quickest Ferrari ever. But
and that thanks to finite element analysis. It's an amazing application of finite element analysis, and
we were looking not only at stresses, but also at compliances and stiffnesses. And trying to optimize every single bit, because of course you could add material like nothing, but with the guidance of the FE simulations, it was done in the parts where it was really needed.
Yeah, I understand. And do you know how many prototypes have been built before to do the testing during this development process?
None.
None,
So
exactly.
only
It is,
numerical.
I ask the question, but it is what I have in mind. It's
Yeah.
so you did the complete development by FEA, and
Yeah.
after that,
Yes. Yes.
they did
Yes. We did the
process.
testing as usual to homologate the
Sure.
dangerous bits,
Yeah.
being the carbon parts, so the wishbones.
Yeah.
These
Yeah.
were clearly anyway done because we were using for the first time high modulus materials to
Mm-hmm.
achieve the stiffness target. So and they are more brittle than
Yeah.
high strength materials.
Yeah. Yeah.
So we
Yeah.
did the testing on those parts, but the metal matrix upright it
Yeah.
went on the car like that. Yeah, yeah.
Very, very interesting. I love what you share, Claudio. Thank you.
It's good to
Especially
remind.
he's talking to me as a huge Formula One fan.
Yeah,
I'm very happy you share this experience. So to continue with the interview, I want to jump into another topic. The landscape of FEA, as you know, has changed dramatically over the years with advances in technology, software, methodologies. So I would like to know from your perspective, how has the role of finite element analysis evolved within your industry or the different industry you work on? And what are some of the most significant changes you witnessed?
yeah. Well, I think non-linear analysis are now much more common, or maybe almost mandatory
Yeah,
everywhere. Maybe if you model an assembly, of course, you would like to have contacts among parts.
yeah,
Whereas a few years ago, you were maybe connecting them with, LB2 kind of elements
yeah,
and stuff like that. And now you tend to put more or less everything. If you have a bolt, it's quicker to model the bolt as a solid rather than, okay, I take this node, put two LB2s, maybe put a beam inside. I still do it from time
yeah,
to
me
time.
too.
Sometimes, sometimes you place the bolt and there it is. You can apply preload, which is something that was not really done in the past, and you were considering the preloading to the bolt calculation by
Yeah,
post-processing the results. So
yes.
for sure, that one is something which is inside. And the
Mm.
funny thing that I realized recently, I went back a couple of years ago into the aerospace field for a company which belongs to Boeing, which is Aurora Flight Science. They
Mm-hmm.
have a site here in Lucerne in Switzerland.
Okay.
I've been there after a few years that I was missing from the aerospace industry, and I realized that they are still doing what they were doing 40 years ago.
I'm not surprised.
Yeah, which is on one side is strange because they have invented the FE. I mean, they have commercialized it through Nastran. It was NASA structural analysis. So they went to the moon with that, and they stayed there. And now you can find much more stimulating, exciting things into the common mechanics from the simulation point of view. I mean,
Yes.
and this is strange on one side, as I said, but it's not so strange on the other side because you are flying people
Yes.
and you need to comply with what is already really known and proven to work rather than trying to do new things. So it's more a much slower process, even for materials. I mean, composites should be the best way to be used in aerospace because of the ratio strength to weight, but they
Correct.
have so many unknowns still in production, in how
Yes.
resin is behaving in time and with the hygroscopic effect. So there are many things which make you think to be really cautious. But for a simulation guy like me, it's not exciting to work for aerospace anymore.
Okay, I understand.
And for the last part of your question, I think it was like what can be in the future. I don't know because 15 years ago, I didn't know where I couldn't imagine that we would have been at this point.
Yeah, it's difficult to predict. Yeah.
What will be in another 15 years, it's difficult to say. You see, we are simulating more or less everything.
Absolutely. Yeah,
So, I don't know, maybe, the real multiphysics, which someone is already doing, will become a common practice. Again, back in the motorsport environment, you do CFD on the wing, which is rigid. Then you pass the pressure distribution to the stress engineers, and you calculate that.
Yes.
And when it's properly done, at least you give back your deformed shape. You get the new pressure distribution 2-3 times just to converge. But
correct.
Most of the times you just say, okay, this is the pressure distribution, this is the stress, we define the laminate, this is the deformation, that's it. But it's actually not what is happening. If you look at the slow motions, I can't imagine that when you see the wing doing like that, it's what you get from CFD or not even from the wind tunnel. Even the wind tunnel models, they're scaled. And you can scale the aerodynamic equations, but you cannot scale the structural equations.
Absolutely.
So you have different deformations and behavior of the model compared to reality. In fact, when you go with the 1-to-1 into the wind tunnel, you get different results.
Absolutely. Yeah, I agree with you, Claudio. I think multiphysics is a key domain for the future in FEA. Absolutely. There are many. Sorry, go ahead.
I did something when I worked for ITER. This international thermonuclear experimental reactor that is being built in France, Aix-en-Provence, close to Aix-en-Provence.
Yeah.
And they have electromagnetic fields which are huge and stressing the structures, but they have also temperature. And so we did some thermomechanical coupled analysis there, because it was so huge that you could have the mechanical forces changing the contact areas, which were in turn changing the heat flow through the parts. So this was almost mandatory, but it's somehow easier because, you add 1 degree of freedom, which is temperature. If you have aero together with the structures.
Exactly. We also do that in the aerospace industry, considering this thermal effect due to the fact that we mix metallic structure with composite structure, which have different CTEs.
Thermal expansions, yes.
Yeah, exactly. So we do those kind of simulation to capture the thermal stresses.
Yeah.
Which is in a sort of multiphysics, because we mix the mechanical effect with the thermal effects.
Okay.
Yeah, thank you for that. There are many engineers out there who are just beginning their journey with FEA, and it is the reason why I started this podcast to inspire them. And based on your extensive experience, what advice would you offer to those who are starting to learn about finite element analysis? Are there any key areas or resources that you would recommend that they focus on for their learning process in FEA?
Well, I would say that the sacrifice of learning the theory is mandatory. So
absolutely,
it has to be done properly at least once. You don't need to become a medical expert, but of course you need to know what is behind, what are the limits, the limitations, what are the boundaries of the method, knowing why the mesh needs to be as it has to be, and knowing how different type of elements do behave with respect to the phenomenon that you want to investigate. So there are things that are also in between the theory and the practice.
Yeah.
And then I think when this is done, there is a huge needing of being really taking a lot of care because of what we said at the beginning. Now you just click one button, you get a mesh, you can mesh everything, you can mesh bolts, you can mesh connection, you have tools which finds directly the contacts between the various parts. they place the contact pairs here and there. You don't need to do almost nothing.
Correct.
But because of that, you need to check
Exactly.
what the calculator, the code is doing.
Yeah.
Because
the sources of errors are everywhere.
Yeah. Because it will run, as we said before, you will get the results, and
Correct.
you might think that because you get the results, then it has to be correct. I'm not even talking about wrong boundary conditions which do not represent the physics of what you were trying to simulate. I'm just thinking about stupid errors that a stupid computer can do,
Yes.
even with the artificial intelligence that I don't really believe in. But
Yeah.
there is still the needing to check on that. One of the best examples, I think, is the units, because every code is unitless.
Absolutely.
I might mention one that I don't know if I can, but there is one which tries to place units inside their graphical interface. And I have a story to tell about that. If you make it wrong, it starts with SI, of course, because meters, kilograms, seconds. But mechanics generally do use millimeters. Then you have to switch to tons for the masses, or change to millinewton for the forces. And so, of course, if you do it with SE, you're not wrong. But sometimes you have some so small distances that the coordinates of the nodes, it will be difficult to do. Anyway, when you realize that you are working in meters, then you say, okay, I change to millimeters. It does everything correct apart from the thickness of the composite.
Oh, okay.
So you were getting something which was 10 meters instead of 10 millimeters.
Oh.
And of course the rest was stretched. And if you don't realize that, okay, this is so big that you see it.
Yeah.
So I prefer to have a system that still let you
absolutely control the units. Yeah.
It's your task responsibility to check a consistent system of units.
Absolutely. Yeah. I like what you say, Claudio, because managing the units, it means that you are doing verifications into your model, okay, before to run the solver, because this management of the unit is done at the pre-processing level.
Yeah.
Okay.
So, yes.
So yeah, totally agree with you.
And then the suggestion, which again is mandatory, try to get an idea of what you will get from your model before you run it.
Absolutely, yeah.
Especially
that's a great advice. Yeah.
At the beginning.
Yeah.
Then maybe when you are experienced, you can maybe just run the model. But still.
Yeah, still having a good idea of the result before to run.
I would say that in the last maybe 5-6 years, I started to, maybe it's a little bit overconfident, over self-confident, or even arrogant what I'm saying, but I started to have the feeling if something was wrong without checking before the order of magnitude, but just looking at the results, saying there must be something wrong. And in general, I was right. So it's probably this is a sort of it's the experience giving you a sort of intuition.
Absolutely, Claudio. Absolutely.
Even if the structure is not something you already did before, so that you have anyway an order of magnitude, but just the behavior of mechanics, looking at the dimensions, materials.
Correct.
There's something telling you, hey, cross-check, double-check, because it sounds like...
Yeah, I can only agree with you, and I love what you say. Personally, I call that the engineering judgment. And I say to the students, use your engineering judgment. And if your engineering judgment tells you something, trust it.
Yeah,
because most 99.9% of the time, your engineering judgment is correct and the software is not. Okay. If there is a mismatch between your engineering judgment and the simulation, you have the good result. You have the good what you believe as an engineer is always the good result. Yeah, definitively. Yeah. I like that. That's a great advice, Claudio. Thank you for sharing that with the audience. I think it's very, very valuable. So yeah, at the beginning of when you started to answer this question, you mentioned learning theory. I think it's fundamental. Not most, but some people are doing FEA without knowing the theory, and I think it's not a good thing.
Yeah, even if it was only one, it was one too much.
Yeah, yeah, but there is more than one.
I have another story about that. This was at Sauber time.
Okay.
I think the stress group didn't have time to look at one thing. It was a pressure vessel for, I don't know if it was the drinking bottle for the driver.
Okay.
I don't remember, something which was not really too much relevant, if you can say that. And the designer said, "Okay, I'll do it. I'll do it with the tool inside CATIA.
Okay.
It's a tool, but it has its limits, and correct. Especially the guy had his limits because he was not trained into stress analysis at all.
Yeah.
So,
and especially if
exactly, he did the thing. It went to production. It didn't even pass through us. We completely overlooked. Okay. They tested it, and it exploded.
Oh.
Okay. So clearly now the problem came back to our desks. We did the model, and it was clear that it would have exploded. We went to him, asked him to see the model, and it was with like elements, huge elements. Yeah. And we told him, why the mesh is so coarse? And he said, it's because if I increased it, the stresses were getting higher.
Oh yeah, we call that convergence. Woo. Okay. Yeah. That's a good example. That's a great example.
Yes. Yeah. So not knowing that, it's the other way around. You need to get the proper stresses, and for that you need a proper mesh, and not getting the mesh that gives you the stresses that you would like to have. It's clearly a limit, of course.
Yeah.
But it was.
And it's a typical example of people who learn FEA just by using a software. Okay, yeah. But learning FEA, it's not that. It's learning the basic theory, learning the modeling techniques, and after that you can learn the software. Okay, so
the software in the end it's a tool.
Exactly. We need the software because without the software, we cannot solve the millions degrees of freedom for sure. So we need to learn the software, but it should not be the first thing to learn when we start learning FEA. Exactly. So it leads me to my next question because for sure when we talk about FEA, we have to talk about software. The choice of the software tools greatly influence the outcome of an FEA project. Which software tools do you prefer for your work, and could you share some insight on their strengths and weaknesses, and how do these tools help you to achieve your goal?
Well, it's a good question, which has, of course, some commercial implications and money, of course, behind that. So back in 2013, when I founded my consultancy company, I clearly needed to look around and decide what software I could have used because, of course, small company, I was on my own at the time. You cannot buy everything. So you need something which could cover more or less everything.
Yeah.
And at that time, I did know many of them. The Altair suite, for example, which was widely used in Sauber, which has the Nastran format as the input file. So That was for sure something I was considering. They also had the ANSYS. I used ANSYS Workbench, which I don't like. By the way, I didn't say it before, I say it now, is the one with the units.
Okay.
And I knew Abacus because I used that back in Ferrari, in Toyota, in Sauber. They had the licenses. They got rid of them because of money. Then they bought it back again for the tire calculation.
Yeah.
Nastran, Patran, Apex. I didn't know. I don't know if Apex was already there at that time. Maybe yes. I don't know. So these are the main that you find in the market nowadays. I'm clearly excluding everything which is included into CAD softwares.
Correct.
And to be honest, despite I learned a lot from Nastran, Nastran was not my first choice.
Okay.
Because for nonlinearities, it was always difficult to deal with, even when they acquired the mark. So you had the Sol 600 instead of the Sol 106, or in addition to the Sol 106.
Yeah.
But still, I found difficult to use it in the end. Preprocessor, apart from Apex, that I crossed it again a couple of years ago. Patran is the classical tool. I worked with Patran for my master thesis when it was not belonging to MSc. But then I think it's difficult to work with, even if it's good old softwares. You create a node, you number a node, you give the coordinates, you can do everything that the other tools allow you to do, but not with that simplicity. So there were the three remaining were Altair suite, but I talked to the guy in Italy, who was the reseller for Italy, because I met him when I worked for Dallara after Ferrari. And he told me that at that time the implicit part of Altair was not good enough, not comparable to Abacus or ANSYS. Then I asked for ANSYS, and I realized that it was costing quite a lot, and you had to add a CAD, what is now space claim, and it was space design at that time. So to modify the geometry to get a better geometry for your meshing. And there was the composite module that needed to be acquired apart, which, by the way, is a little mess, in my opinion, the way it handles the layer generation, etc. So it remained Abacus. This was the way, because in the end, I could buy a license running on one CPU for 15 or 16,000 euros per year. And you had the pre-post, you had implicit, explicit, if you can run explicit with one CPU, of course. You had the composite module inside, so you had everything. The only limit was the number of CPUs that you could use. So in the end, I went for that. And a few years later, they proposed me to acquire really the license. So I bought it. So I had more CPUs, more CAE for the pre and post processor licenses. So we could work more than one guy at a time. And I think it's still the best compromise, because of what I said. You had a CAD part which can manage geometries. You can build geometries. You can modify geometries quite quickly. It has a good measure.
And is it Abacus standalone or into 3DX?
Sorry?
Is it Abacus in standalone or into 3DX?
It's no. I think now they switched anyway to the 3D experience.
3D experience, exactly.
Yes, but I think it's
part of the Simulia series.
Yes, but you can still have the only Abacus, so you don't need to have CATIA. You still have this pre-processor, which looks like CATIA, but it's not.
Okay.
And you have your solver apart.
Okay. See, it is. I think it is what they call the standalone.
I think so. Yeah.
Okay. Interesting.
And you have the composite module, you have the topological optimizer, size optimizer, shape optimizer. So everything is included there. Explicit, as I said. So it costs if you buy the license. It costs, but I think it is worth. And you can more or less cover everything. On top of that, who has Altair suite can read in your input files and your result file.
Yeah.
So you can also work with people that do have Altair. I had some troubles to work with the Swiss aerospace company, the RUAG, which is now called Beyond Gravity, because they wanted everything with Nastran. But in the end, they were linear calculations, so I showed them that the results were the same, so they were happy. But they wanted anyway to convert the files into the Nastran format to get everything there. So for me, this would be the way to go. But Calculix and PrepoMax and MacWay is not really completely free, but you can have an unlimited license for $350, which is nothing. PrepoMax, I think this guy is doing a great job.
Yeah, agree with you.
And very impressive. I know it since years. I think that Guido don't is crazy just releasing software like that.
Here we are talking about the open source solutions.
Yes.
I agree with you. The Calculix, PrepoMax, and I would like Codaster, but Codaster is not user friendly compared to PrepoMax. But good open source solutions anyway.
Yes, Codaster is for sure. It's developed since years by Énergie de France. They built nuclear plants with that.
Correct. But I think we can say that it's accurate and reliable.
The problem is the pre and post. Really.
Absolutely.
Salom, how is it called?
Correct.
It's a disaster. So
correct.
If someone really started to develop pre-post for Codaster, that would be also another really valuable code.
Absolutely. Yeah.
But for me, Calculix is a great option because it has 90%, 95% of the input file like Abacus. So they're the same naming. So now that it's 20 years I'm using Abacus.
It's easy to switch between the two.
Yes, exactly. And I think it's something which it should be pushed on because in the end, as I said, if you are a consultant, you cannot afford a full Abacus license.
No.
It's crazy.
It's you're right. The software prices are extremely high, so it's very difficult to buy the complete suite of.
Luckily enough, at least the hardware went down. It doesn't cost so much as it was 20 years ago, and you run huge models on a laptop. In the end,
absolutely.
Laptop, but still a laptop.
Thank you for sharing your thought about software. Very interesting for you. So we are close to the end of this interview, but I would like to talk with you. You mentioned it during the other question to answer the question, but I want to talk about validation and verification because we know that they are critical aspects of FEA to ensure the accuracy and the reliability of the results. What is your approach to validating and verifying your FEA models? And are there any specific techniques or best practices that you follow?
I have to highlight that the next words is just a joke. And I will say that reality is wrong, the model is right.
Excellent.
Which is totally the opposite of what we were saying before. No, for sure, there are a few things. Well, in the past, there were many more things that you needed to check. And indeed, in the aerospace, you had a sort of checklist with all of the things that you should ask to Nastran to check for you. The max ratio, so the ratio between the terms in the matrix, the minimum and the maximum, which needs to be. Someone was already also giving a limit to that. So you
Correct.
needed to verify that, and if you were out, you needed to redo your mesh, check where it was the problem. So this for sure, there are some software checks that you need to do. Well, reaction forces, of course, this is the main topic. But as I said, some of them are less important now because of the numerical precision of the codes. Now
That's
we are
correct.
4 bits, and I think Algor was possibly 8, maybe 16. So clearly, the element distortion, for example, which is giving some strange results because it changes the max ratio, or anyway the quality of the matrix, is not so important anymore.
Yeah.
You know one thing, I maybe mentioned something in the first release of the book. I was trying with Algor deforming an element to become unmanageable, giving numerical errors. So like having more than 180 degrees on a C quad, which is clearly wrong. When I did the new release, I tried to do the same example with Abacus. It's not possible. It gives you some results, even the angle is more than 180 degrees. I don't know exactly what it does, but because it's difficult to see only on one element what you're looking for. But while with Algor, it was clearly giving results like I'm pushing up the node and the node is going back. So this is clearly wrong. In this case, you're pushing it up and it still goes up. So you cannot say by how much it's wrong. It's clearly wrong, but you cannot mention that. So all of these things are less important. But despite that, some companies still do ask them, and it's probably a good practice to do it. The other one is the rigid motion. So you take your model, you just apply a constant translation to one node and see that everything is moving. So no strain energy. Same for the rotations.
Yes.
Then also the ratio between the maximum and the minimum in a free modal analysis, eigenvalues has to be below a certain value, which is also given. So there are some numerical checks that you can do and you should do. Yeah. Especially maybe when you need to gain confidence with the code and if you're new to the practice. And then there are clearly the testing validations where you strain gauge your thing, you go to ultimate. I always said that, I still say that failing a part in a laboratory, of course, it's a huge source of learning.
Yes.
And some teams, like for example in Sauber, they didn't follow really this philosophy, and they didn't want to fail. But I mean, you've ended the test. You're not going to put this part on the car. Just break it. We see where we are. It's strange, but
you're right. Validation testing. It's like a philosophy of company, and not all companies have this philosophy.
But it's where you learn, and it's still the interesting part. I was working for a project now with an Italian company for I cannot say that because it won't go well. We don't know what it will be the end of this car. It was a high performance electric car. And I was in charge of the halo. It's not running in any formula. So, but they wanted to comply with the Formula One regulations. I did the halo in composite, which in Formula One is not allowed, and the real rope. So for the safety of the driver. And that one was done in 3D, printing. And I said, okay, now we did everything because some plastification is allowed.
Yes.
We went over the elastic limit because clearly you want it's on the high part of the car, so you want to be as light as possible. And I said, okay, now it's done. We did the calculations. You're going to produce it. Then tell me when you test it because I want to join. And the guy in charge of the project said, strange. No stress engineer wants to join the tests. I said, yes, it's probably where you don't want to be, but I feel like you have to, because you did everything. That the thing is built following your indications, and you have to be there if it fails.
But it's a typical example where there is no regulation. there is no regulation which for them to do the test in order to validate the simulation, which is completely different in the aerospace industry, because in the aerospace industry, it's mandatory. If you want the certificate of navigation, you have to do this correlation. Yes. And it's a huge advantage, because as soon as you do the correlation, you can tweak the model, adjust the model in order to match the reality. And after that, you have a very powerful tool. You can build, you can simulate after that. You can do optimization, because you know that the model is right.
Yes.
You can do optimization. You can simulate repair, stuff like that. You can simulate everything, all the new design, because you did this validation. So
this is the good part of simulation in aerospace.
Yeah, absolutely. Totally agree with you. Totally.
Connecting to what I was saying before, for simulation probably is not that much, but when you come to correlation, then you have the testing and you are forced to do it, as you said, because you have to get the certification. Then you are forced to match or try to match your model with the results. Yeah,
correct.
That's the. It's a boring part on one side, but it's
You're right, but it's very satisfying at the end of the day when you obtain a model matching the reality. You know, and you learn a lot on the modeling technique, because you learn. You learn what you have to do precisely in order to obtain the reality. So
it's like doing homework.
Correct.
It's boring, but it's what it's forming you. So
I would like to conclude this interview, Claudio, coming back to your book, Computational Structural Engineering. To be honest, as I said at the beginning, I enjoyed a lot reading this book. I would like to know what inspired you to write it, okay? And what key message, or I should say insights, do you hope to convey to your readers through this work? What do you wish for them to take away from your book?
I think it comes from when I started working in FE professionally. As I said, I had this guy this consultant in the railway company who taught a lot to us. If he was not there, then I think I would have struggled to get on the right path since the beginning. Because when I came out from university, unfortunately, I knew everything about theory, but nothing about practice. So nobody told me what is a rigid element.
Okay.
Nobody told me how to constrain a thing or to simulate a bolt or whatever. We knew everything about the Jacobian's shape function, which is good. You need to, but you need also to know how to do when you do practice. So I started writing articles in the end for a couple of technical magazines on some aspects, just monographies and saying, okay, this is the problem and this is how you face it with FE. Okay. And then at a certain point, I thought, well, why not to collect them into a book? And I started looking to publishers, and everybody was asking me, okay, yes, we can do it. Where are you teaching? What are you teaching? I said, I'm not a teacher. So, and the guys were saying, so how can you guarantee that you sell a certain number of books? Which is awful to say, but this was the case. I was close to giving up. And then when I was in Ferrari, in Modena, there was one guy who had a publishing company, mainly for, or maybe only for the medical side, and he was trying to enter into the engineering. So he said, okay, we do that, but we share the cost of printing 500 copies. And this is what we did. I did my calculations based on what he would have given me as royalties and based on what I was paying. And with 500 copies, I would have not even covered the cost of that. But I wanted to do it. And I did it. And in the end, it was sold quite quickly. And so we printed again another 1,000 copies. So I could cover my costs. And then the second one came. Which was with more advanced stuff, with non-linearities, composites, etc. And then they stayed there for years. The interest was clearly going down because if you have nothing new on the market. And then with the COVID, I had a drop into the professional activity, and it was the time to just go back and redo everything. So in 1 year and a half, I redid all the examples with Abacus, one code. I put everything together, more organized. I added a lot of things. I think it's from 40 to 50% more stuff than there was before. And this was done. I went to the same guy who gave the company off, so he was retired, but he was still collaborating with another publisher in Naples, Italy. And we went for that. And I kept the rights for the English version, which is published on Amazon. And to be honest, I think it's even better in terms of quality of the paper. The colors are much more brighter than the Italian version. The paper is thicker. And given that it is a print on demand, I could catch up with some stupid mistakes that are always there, of course. And that's it. I contacted last year Springer, which is a German international publisher. They are interested, but not in republishing this, of course.
Okay.
So they said with 10-20% more stuff, we could think of a new edition, and they would do it differently. They would do it electronically to be sold in universities, so in libraries in the university, so that the students can take for a while, for what they need, just electronic copy. They will print also paper copies, but it would be more spread around. It's difficult on Amazon.
Correct.
For sure, see my posts in LinkedIn. Probably I'm boring people and get them annoyed. But,
you have no choice. You have no choice. You have to do it.
Exactly. It is that. But and I like writing in the end, doing these kind of things. So the idea, coming back to the beginning of the question, is to try and guide someone who already knows the theory to get the good practice. And I'm trying whenever possible to compare the results with analytical or semi-analytical or semi-empirical results. And when it's not possible, you clearly rely on the FE, like fracture initiation. You could do it with fracture mechanics, and it would be possible. And maybe it's an idea for the next edition.
Correct, exactly. Excellent. Thank you very much, Claudio, for sharing all those thoughts. It's very interesting. I'm pretty sure that the audience is going to love this episode, because it's a lot of very good content, a lot of very good insights. So thank you very much, Claudio, for taking time to answer the questions.
Thank you.
Bye-bye.
Bye, Dominic.